turbopump if you have very cold propellant. Really one of the keys here, though, is the vacuum version of Raptor having a 382-second ISP. This is really quite critical to the whole Mars mission. And we're confident we can get to that number, or at least within a few seconds of that number, ultimately maybe exceeding it slightly. So the rocket booster, in many ways, is really a scaled-up version of the Falcon 9 booster. You'll see a lot of similarities, such as the grid fins, obviously clustering a lot of engines at the base, and the big difference really being that the primary structure is an advanced form of carbon fiber as opposed to aluminum lithium, and that we use autogenous pressurization and we get rid of the helium and the nitrogen. So this uses 42 Raptor engines. It's a lot of engines, but we use 9 on a Falcon 9, and with Falcon Heavy, which should launch early next year, there's 27 engines on the base. So we've got pretty good experience with having a large number of engines. It also gives us redundancy, so that if some of the engines fail, you can still continue the mission and be fine. But the main job of the booster is to accelerate the spaceship to around 8,500 kilometers an hour. For those that are less familiar with orbital dynamics, really it's all about velocity and not about height. So really that's the job of the booster. The booster is like the javelin thrower. Sort of, it's got to toss that javelin, which is the spaceship. In the case of other planets, though, which have a gravity well which is not as deep, so Mars, the moons of Jupiter, conceivably one day maybe even Venus. Venus will be a little trickier, but for most of the solar system, you only need the spaceship. So you don't need the booster if you have a lower gravity well. So no booster is needed on the Moon, or Mars, or any of the moons of Jupiter, or Pluto. You just need the spaceship. The booster is just there for heavy gravity wells. And then we've also been able to optimize the propellant needed for boost back and landing to get it down to about 7% of the liftoff propellant load. We think with some optimization, maybe we can get it down to about 6%. And we've also are now getting quite comfortable with the accuracy of the landing. If you've been watching the Falcon 9 landings, you'll see that they're getting increasingly closer to the bullseye. And we think, particularly with the addition of some thrusters, some maneuvering thrusters, we can actually put the booster right back on the launch stand. And then those fins at the base are essentially centering features to take out any minor position mismatch at the launch site. So it looks like at the base. So we think we only need to gimbal or steer the center cluster of engines. So there's 7 engines in the center cluster. Those would be the ones that move for steering the rocket, and the other ones would be fixed in position, which gives us the best concentration of we can max out the number of engines because you don't have to leave any room for gimbaling or moving the engines. And like I said, this is all designed so that you could actually lose multiple engines even at liftoff or anywhere in flight and continue the mission safely. So for the spaceship itself, in the top we have the pressurized compartment, and I'll show you a fly-through of that in a moment. Then beneath that is where we'd have the unpressurized cargo, which would be really flat-packed in a very dense format. And then below that is the liquid oxygen tank. The liquid oxygen tank is probably the hardest piece of this whole vehicle because it's got to handle propellant at the coldest level, and the tanks themselves actually form the airframe. So the airframe structure and the tank structure are combined, as it is in all modern rockets. And in aircraft, for example, the wing is really a fuel tank in in wing shape. So that it has to take the thrust loads of ascent, the loads of reentry, and then it has to be impermeable to gaseous oxygen, which is tricky, and non-reactive to gaseous oxygen. So that's the hardest piece of the spaceship itself, which is actually why we started on that element as well, and I'll show you some pictures of that later. So, and then below the oxygen tank is the fuel tank, and then the engines are mounted directly to the thrust cone on the base. And then there are 6 of the high efficiency vacuum engines around the perimeter, and those don't gimbal. And then there are 3 of the sea level versions of the engine which do gimbal and provide the steering. Although we can do some amount of steering if you're in space with differential thrust on the outside engines. The net effect is a cargo to Mars of up to 450 tons, depending upon how many refills you do with the tanker. And the goal is at least 100 passengers per ship, although I think ultimately we'll probably see that number grow to 200 or more. This chart's a little difficult to interpret at first, but we decided to put it there for people who want to watch the video afterwards and sort of take a closer look, analyze some of the numbers. The column on the left is probably what's most relevant, and that gives you the trip time. So depending upon which Earth-Mars rendezvous you're aiming for, the trip time at 6 kilometers per second departure velocity can be as low as 80 days. And then over time, I think would obviously improve that, ultimately I suspect that you'd see Mars transit times of as little as 30 days in the more distant future. So it's fairly manageable considering the trips that people used to do in the old days that routinely take sailing voyages that would be 6 months or more. So on arrival, the heat shield technology is extremely important. We've been refining the heat shield technology using our Dragon spacecraft, and we're now on version 3 of Pica, which is phenolic impregnated carbon ablator, and it's getting more and more robust with each new version, with less ablation, more resistance, less need for refurbishment. The heat shield is basically a giant brake pad. So it's like, how good can you make that brake pad against extreme reentry conditions and minimize the cost of refurbishment, and make it so that you could have many flights with no refurbishment at all. So this is a fly through of the crew compartment. I want to give you a sense of what it would feel like to actually be in the spaceship. I mean, in order to make it appealing and increase that portion of the Venn diagram where people actually want to go, it's got to be really fun and exciting, and it can't feel cramped or boring. So the crew compartment or the occupant compartment is set up so that you can do zero-G games, you can float around. There'll be like movies, lecture halls, your cabins, a restaurant. It'll be like really fun to go. You're gonna have a great time. So we've got the propellant plant on Mars. Again, this is one of those slides that I won't go into in detail here, but people can think about offline. The key point being that the ingredients are there on Mars to create a propellant plant with relative ease. Because the atmosphere is primarily CO2, and there's water ice almost everywhere, you've got the CO2 plus H2O to make methane CH4 and oxygen O2, using the Sabatier reaction. The trickiest thing really is the energy source, which we think we can do with a large field of solar panels. So then to give you a sense of the cost, really the key is making this affordable to almost anyone who wants to go. And we think based on this architecture, assuming optimization over time, like the very first flights would be fairly expensive, but the architecture allows for a cost per ticket of less than $200,000, maybe as little as $100,000 over time, depending upon how much mass a person takes. So we're right now estimating about $140,000 per ton to the surface of Mars. So if a person plus the luggage is less than that, taking into account food consumption and life support, then we think that the cost of moving to Mars ultimately could drop below $100,000. So funding, we thought about funding sources, and so we've got steel underpants, launch satellites, send cargo to the space station, Kickstarter, of course, followed by profit. So obviously it's going to be a challenge to fund this whole endeavor. We do expect to generate pretty decent net cash flow from launching lots of satellites and servicing the space station from NASA, transferring cargo to and from the space station, and then I know that there's a lot of people in the private sector who are interested in helping fund a base on Mars, and then perhaps there will be interest on the government sector side to also do that. Ultimately, this is going to be a huge public-private partnership, and I think that's how the United States was established, and many other countries around the world is a public-private partnership. So I think that's probably what occurs. And right now we're just trying to make as much progress as we can with the resources that we have available, and just sort of keep moving ball forward, and hopefully I think as we show that this is possible, that this dream is real, not just a dream, it's something that can be made real, I think the support will snowball over time. And I should say also the main reason I'm personally accumulating assets is in order to fund this. So I really don't have any other motivation for personally accumulating assets except to be able to make the biggest contribution I can to making life multiplanetary. Timelines. I'm not the best at this sort of thing, but just to show you where we started off, in 2002, SpaceX basically consisted of carpet and a mariachi band. That was it. That's all of SpaceX in 2002. As you can see, I'm a dancing machine. Yeah, I believe in kicking off celebratory events with mariachi bands. I really like mariachi bands. But that was what we started off with in 2002. And really, I mean, I thought we had maybe a 10% chance of doing anything, of even getting a rocket to orbit, let alone getting beyond that and taking Mars seriously. But I came to the conclusion that if there wasn't some new entrant into the space arena with a strong ideological motivation, then it didn't seem like we were on a trajectory to ever be a spacefaring civilization and be out there among the stars. Because in '69 we were able to go to the moon, and the space shuttle could get to low Earth orbit, and then obviously the space shuttle got retired, but that trend line is down to zero. So I think what a lot of people don't appreciate is that technology does not automatically improve. It only improves if a lot of really strong engineering talent is applied to the problem that it improves. And there are many examples in history where civilizations have reached a certain technology level and then have fallen well below that, and then recovered only millennia later. So we go from 2002, where we basically were clueless, and developed with Falcon 1 the smallest useful orbital rocket that we could think of, which would deliver half a ton to orbit. And then 4 years later, we developed and built the first vehicle. So we developed the main engine, the upper stage engine, the airframes, the fairing, and the launch system, and had our first attempted launch in 2006, which failed. So that lasted about 60 seconds, unfortunately. But 2006, 4 years after starting, is also when we actually got our first NASA contract. And I just want to say I'm incredibly grateful to NASA for supporting SpaceX, despite the fact that our rocket crashed. It was awesome. I'm NASA's biggest fan. So thank you very much to the people that had the faith to do that. Thank you. So then, 2006, followed by a lot of grief, and then finally the fourth launch of Falcon 1 worked in 2008, and we were really down to our last pennies. In fact, I only thought I had enough money for 3 launches, and the first 3 bloody failed, and we were able to scrape together enough to just barely make it and do a 4th launch. And thank goodness that 4th launch succeeded in 2008. That was a lot of pain. And then also at the end of 2008 is when NASA awarded us the first major operational contract, which was for resupplying cargo to the space station and bringing cargo back. Then a couple of years later, we did the first launch of Falcon 9, version 1. And that had about a 10-ton to orbit capability, so it was about 20 times the capability of Falcon 1. And also was designed to carry our Dragon spacecraft. Then 2010 is our first mission to the space station, so we were able to finish development of Dragon and dock with the space station in 2010. 2010 is expendable Dragon. 2012 is when we delivered and returned cargo from the space station. 2013 is when we first started doing vertical takeoff and landing tests. And then 2014 is when we were able to have the first orbital booster do a soft landing in the ocean. The landing was soft, it fell over and exploded, but the landing, for 7 seconds, it was good. And we also improved the capability of the vehicle from 10 tons to about 13